Please. Don't be kidding if you don't leave I did less in my
Sorry, I felt like I was just like leaving for a moment, but I saw someone else come over, so I just followed back at him. I was like, oh, good. Yeah, I saw someone else come start looking kind of lunch, so we should be talking.
Okay, to speed up things, I'm going to introduce myself. I'm I'm actually surprised to see so many people here, because if there would be just a few people from George Washington, we could go straight to the happy hour. But since you are here, I'm going to give that talk. Okay, so I'm actually faculty at the George Washington University here, doing high energy astrophysics. My interests are, used to be for a long time in neutron stars, but now they're a bit broader. It's including the unidentified gamma ray sources, GRBs, microquasars, that kind of stuff. So it's really hardcore, high energy, stuff. Today, just a couple words about the department, actually, in case you're interested. So the department is a physics department. It's not large. It's about 18, right, Kalvir faculty? Or?
Depending how you count, yeah, 21.
All right, about 21 faculty, and of them, maybe 3-4 really doing astrophysics. And it's all high energy astrophysics. So we try to stay really focused here. And so there's a big interest in GRBs in particular, and in the neutron stars, compact objects, and very high energy sources. Those are sort of the main directions here. All right? So if you are interested in that kind of science because you want to collaborate simply, you're doing something similar and you want to collaborate, or you want to take a course, for instance, in high energy astrophysics, because I'm teaching high energy astrophysics not every semester, but I'm teaching it. You can probably arrange to take this course even if you are at a different university, like UMD. Or if you are an undergraduate student and interested in some graduate program at GW, just email me and we'll talk. Right? So today I'm going to speak specifically about neutron stars. In particular, I'm going to be talking about isolated neutron stars. So many of you heard about the accreting neutron stars. So I'm not going to be talking about the accreting neutron stars. There is a complex business there involved with this donor star, which can be of a different kind. It can be, there's a whole different set of physics. We are trying to look at something simpler here, which is just an isolated neutron star. And even that turns out to be, extremely diverse and complex object, and very interesting. So even when we are talking about isolated neutron stars, we should distinguish a few flavors of those objects. And the most famous one is actually rotation-powered pulsars. So those are the ones which have been discovered 50 years ago accidentally when they thought they found the green man, but that was a pulsar. So those have been around for a while. And then all these other flavors of neutron stars, they actually appeared in the past maybe 20 years. And the next one was the soft gamma ray repeaters. It's also maybe dates back about 30 years as an observational phenomenon, but it's only very recently we gained some deeper insight in what kind of object it is. Right, so, and the additional class of objects which is related to the soft gamma ray repeaters is called anomalous X-ray pulsars. And so this whole both of these types of objects are neutron stars, and they're actually extremely magnetized neutron stars. So the neutron stars are, by definition, they have very strong magnetic fields, 10 to the 12 Gauss. But these guys have magnetic fields which are a factor of 100 larger even. So that's why they're called magnetars. And then there are two types which have been discovered only very, very recently with Chandra, essentially, X-ray observatory. And those are the neutron stars which like to live in young supernova remnants right in the middle. They don't like to move around. They have very small velocities for some reason, and they stick right in the center of a young supernova remnant. They also have they have a low, by neutron star standard, they have low magnetic fields, a factor of 100 lower than in the standard rotation-powered pulsars. And then there's the strange objects which I actually seen only very rarely through the spikes in the radio. They called rotating radio transients. We think those are the neutron stars because we were able to measure a few periods for these guys, but they're very intermittent. You don't see them most of the time. So the rest of the talk, I'm going to be talking mostly about the rotation-powered pulsars and maybe one or two slides about the magnetars, because there is just not enough time to cover those. So for the purposes mainly of education, but also because it's shown in every talk on pulsars, this is so-called PP dot diagram. And that's because the main property of the pulsar is actually its period. So how fast the neutron star is rotating. And the second main property is actually how fast it is slowing down. Because the neutron star tends to lose energy through either radiation or wind of extremely energetic particles, it loses energy. And so that translates into the spin down, what's called spin down. It rotates slower, slower, and slower. We are talking about isolated neutron stars here. And so when you measure the spin down rate and the actual spin period, you can put all these neutron stars, all known neutron stars, on this diagram. And what happens then is that the small black dots, which is majority of data points here, are the rotation-powered pulsars. And you see that is the largest population here. And then there are other kinds of objects like magnetars and those rotating radio transients and something else. And there are very few of them. And they live in a different part of this PP dot diagram because they have much stronger magnetic fields in the case of magnetars. They have low magnetic fields in the case of those central compact objects which live in supernova remnants, and so they differ, apparently. So the fact that there are few of them here does not mean that there are actually fewer of them, because it may be just an observational bias. There are reasons for which these objects may be difficult to detect because they may be not always on, say, in X-rays, like for the anomalous X-ray pulsars, because they can be transient objects, or for soft gamma ray repeaters. So you see them only once in a while. Now, talking about the standard pulsar picture, the rotation-powered pulsar, what is distinct for this kind of star is, as you can guess, a magnetic field. Which is very strong for neutron stars. So the neutron star itself is this very tiny little dot in the middle, which you cannot see, and all what you see here is the big magnetosphere. And the magnetosphere is actually, it's not only magnetic field. If you have a rotation, and all these guys, they rotate pretty fast, if you have a rotating magnetic field, you can produce electric field in such system. And the electric field will be also very strong because the magnetic field is strong and rotation is fast. And so what happens is that electric field extracts particles from the surface of the neutron star, like electrons, and accelerates them to very large energies, Lorentz factors of about 10 to the 4. So we are talking about extremely relativistic particles. When you do that in this magnetosphere, what happens is that the cascade of particles is initialized. And so one particle can give birth to, let's say, up to 1 million particles, which will have lower energies, of course, but they're still going to be relativistic. And all this cascade is multiple, it's actually multiple cascades. So so you produce from one particle, two particles, they produce more and more, and so you can multiply. It's called multiplicity parameter. You can multiply by a factor of 10 to the 5 or maybe even 10 to the 6. So you populate the magnetosphere with these charged particles, which are still relativistic. They move in the magnetic field, and then what happens? They radiate. They radiate synchrotron radiation. They radiate curvature radiation. And that is what we see at higher energies. In the optical, in the X-rays, in the gamma rays, we may be seeing some of the inverse Compton scattering. Now, in the radio, we don't know why they radiate. So it's radio pulsars. They were discovered first, but we don't know what process is responsible for the radio emission from the pulsars, despite it's been 50 years. All we know is some kind of coherent mechanism, emission mechanism, so which is different from the usual synchrotron and curvature radiation. So I'm not going to be talking about that kind of emission because it's still a mystery, and so what we've done is since the Chandra was launched and Fermi came online and the actually Veritas came online, we tried to study these objects at higher energies. And so this is a little bit different. It's the same PP dot diagram, but what it shows here is a population of objects detected at higher energies. And so the red dots are the pulsars detected in X-rays, and the blue dots are those detected at gamma rays by Fermi. It's a little bit outdated by about 1 year, so there are many of them, more of them now, but more or less that's the picture. So you tend to detect younger pulsars which live there. So younger neutron stars with large, energetics, because they spin fast, they have strong magnetic field, and they tend to live in this corner. And they're nearly all detected in the gamma rays and X-rays. And this clump of stars is actually millisecond pulsars, which is something I probably won't be talking much today, but they are extremely old pulsars. They actually used to be accreting pulsars at some point in the past. So they used to be member of a binary. And then either they actually completely ate the other star, they just consumed it, or somehow got separated from the other star, but they are spinning really, really fast, and they're very old, and they tend to have lower surface magnetic fields. So they live separately a bit. So what happens in the, how do those objects actually operate? What do they do? And so we talked about the magnetosphere, the electric field, and then there is this relativistic particles in the magnetosphere, right? So that's we mentioned. And then beyond the magnetosphere, you have, some of these particles leak out of the magnetosphere, and they form pulsar wind. The pulsar wind escapes actually into the interstellar medium. Then there is this magnetospheric emission from inside magnetosphere, as I mentioned, synchrotron and curvature at higher energies, and who knows what in the radio. And then there is another component, which is actually not due to the particles. It is the surface of the neutron star itself. And this is quite an interesting component. And so it turns out that actually all of these, they do produce X-ray radiation. So for instance, not necessarily all of these produce gamma ray radiation. For instance, just thermal emission from heated polar caps or hot surface, it's not hot enough to produce any gamma rays. So, but in X-rays, all of these components matter, right? So I'm just going to try to talk a little bit in more detail about these different components. So there is this non-thermal emission from the magnetosphere and thermal from the surface. That means the spectrum, if you take a multi-wavelength spectrum, so this is a log of frequency in hertz, of a neutron star, typical pulsar, it might look like that. It would look like a power law, which is definitely non-thermal something. Now the question is, how that power law behaves across all this frequency range. So we know the Fermi measurements here indicate cutoff and some power law. Then we know X-rays. X-rays show some kind of power law here, and then maybe in the optical also. Do they connect these components, or they due to different radiation processes? That's not quite understood. They were expected to be due to different processes, but there is evidence that they actually can connect nicely and form a single power law. So it's puzzling a little bit. And this bump here is the thermal emission from the neutron star surface, which is actually in the soft X-rays, and that's because the temperature is such that the Planck spectrum maximum corresponds to the soft X-rays. And so why is that, what can we extract out of that? Out of that, we can look and fit, the thermal spectrum with some kind of black body. The simplest thing is a black body, Planck spectrum. We measure the temperature from the feet, and that's the temperature, hopefully, of the neutron star surface. Now, as you know, neutron stars are something that we don't really know. We know the surface layers, probably iron, maybe with some small cover, thin layer of atmosphere of hydrogen accreted from the interstellar medium. But what's really deep inside, we can't even say, because at some point the theories which can be used to predict the equation of state at those densities are a factor of 5 larger than nuclear density. And we don't really have reliable theories which we tested in the labs at those densities. So we don't know the state of matter there. So there's some hypotheses and assumptions like free quarks or something like that. One way to test what is really inside is to measure the surface temperature, because how fast the neutron star cools depends on the equation of state. It depends on what kind of matter you really have inside, as well as the radius of the neutron star depends on that. And so by measuring the thermal spectrum, we can constrain the properties of the matter at supernuclear densities. That's why it's interesting to measure those temperatures. And those are the constraints on the cooling, or you can put it, in other words, on the equation of state of that matter you can get from those kinds of feeds. Now, I'm just going to quickly go through recent results of many of them I actually obtained myself. So this is a recent detection of something famous, something unique. It's called double pulsar. So there is only one system where you have two neutron stars orbiting each other, and both of them are pulsars. It was recently discovered. It's got very famous because it can be used for testing general relativity, because you have two very accurate clocks orbiting each other, so you can do a lot of great tests for the general relativity. But what was also interesting, this is one of the few neutron stars which we were able to detect in the far ultraviolet. That's not where you normally can detect a neutron star. Most of them are detected in X-rays or gamma rays. So this is one of the few cases. And okay, so maybe that's interesting, but so what? The reason for excitement is that we also can estimate the temperature of the neutron star surface, in this case, from the measurements in the far ultraviolet. So we assume a black body kind of spectrum, Planck spectrum, and in this regime, this tail of the black body spectrum is called Rayleigh-Jeans tail, right? And so if you match it to the observed points and you assume normal, reasonable neutron star radius of 10, 13 kilometers, the temperature you get is rather high. It is approaching around 1 megakelvin. Now, so what? So some of them emit in X-rays, so they're even hotter. Why is that interesting? The reason why it's interesting is that the both pulsars in this system, they are old. They're quite old. They are about 100 mega years old. At that age, you would think that the neutron stars should cool. They should be much colder than this temperature that we see here. So how do they manage to remain so hot? There's some kind of a heating mechanism required to keep them hot, most likely. Or we don't understand the interior of the neutron star completely. And so it's actually, I'm going to mention the other case where we have an interesting measurement of the temperature. So that's why I think that's an important result. Now, returning to the magnetospheric radiation, the non-thermal radiation, that was about thermal radiation. The other recent result is that we try to connect the Fermi power law with the low energy power laws, and we see that they sort of, if you draw a line here, amazingly it goes through this X-ray power law, it goes through the optical, and it goes through the Fermi. So it doesn't have to go through all three. I mean, in principle it could be whatever, but there are 6 objects for which we have multi-wavelength measurements, and when you draw a line between that end and that end, this end falls onto that line, which is saying that maybe the previous interpretation of the spectrum, multi-wavelength spectrum, as a curvature or inverse Compton emission at the higher energies and the synchrotron at lower, maybe it's not quite right. So there's something to think about here. Okay, I apparently died. All right, let's skip through this slide. Now, this is a case of the another pulsar. This pulsar is very interesting because it's actually nearby. It's just 200 parsecs away. So you can fly there. If the NASA eventually finds money to build a spaceship which goes at the speed of light, it's only a couple hundred years to get there. But if you go into this relativity stuff in your reference frame, that's going to be just a year, so no problem. So this pulsar is also interesting because in addition to this non-thermal, and thermal component, it has some kind of features apparently in the optical spectrum, which is not something expected from the neutron star, really, because it's supposed to have condensed surface and maybe magnetosphere. So maybe there is some thin layer of kind of like atmosphere on top of that solid surface. Why is that interesting? Okay, there is atmosphere. It's interesting because it provides an independent way to measure magnetic field and the surface. If you have absorption features, for instance, they may be cyclotron harmonics. And if you're talking about the cyclotron harmonics, then you can measure the surface magnetic field, and that's nice, right? And so we found those kind of features in maybe already 3 objects, and that happened during the past 3 years, I would say. And so this is one I personally worked recently on. And you see those features are actually variable. They vary with the pulsar rotation phase. And what's happening here, maybe, is that your neutron star actually rotates, and the whole magnetosphere is sort of rotating, right? And if the magnetosphere has some kind of a belt, like a radiation belt around the Earth, then the line of sight to the telescope may be crossing or not crossing that belt. And so at some occasions, like when it's crossing, you may see these absorption features. And when it's not crossing, you wouldn't see the absorption features. So that provides a test of the structure of the magnetosphere. Let's keep that complexity there. That's the other interesting case where we looked at the far ultraviolet with Hubble Space Telescope again, and a neutron star, which is even closer. It's just 140 parsecs away, a very lucrative thing to fly a starship to. And so it's even older. It's half the age of the universe. Okay, if that one's supposed to be cold, I was talking before about another one, at 50 mega years. That one is 5 giga years, half the universe age. So supposed to be rock cold, right, completely. Now, we think we measured the surface temperature of this neutron star because we detected radiation in the far ultraviolet, and it is consistent with the relay Jeans kind of spectrum at the temperature of 100,000 Kelvin. So, how do you keep it warm? And so, I don't know, there are all kinds of hypotheses have been suggested, from accretion of dark matter to some kind of complex processes in the nuclear matter inside the neutron star. Now we just got accepted the Hubble proposal to study 3 more very old neutron stars this next year. And so we are really looking forward to some exciting results. Right, so I was talking about this thermal emission from the neutron star surface a lot. And actually, in the recent years, there is an interesting model which suggests that you should take into account magnetic field when you're talking about the neutron star cooling. Not only what kind of matter you have inside, quarks or not quarks, hyperons or whatever, but you also need to think about magnetic field in the crust because it actually decays there and it produces some heat in the crust. And it's called magnetic thermal evolution of neutron stars. And so those with the higher magnetic fields, they should be hotter. And those are the models, but what's important are, say, this plot, which shows how the neutron star with this magnetic thermal evolution should cool down as a function of age. So this is the thermal luminosity as a function of age. And so indeed, we see that those magnetars, the ones with very large magnetic fields, they kind of tend to be hotter. They have higher thermal luminosity. And the other stars are cooler. So that has only appeared in the past, say, 3-4 years. I wasn't talking about magnetars because of the lack of time, but these are very interesting guys. For instance, this was a random kind of observation with Chandra. We were looking some supernova remnant, and there's not much really there. We wouldn't pay attention to this point on the sky, really. There's not much there. And so 5 years later, there was a very bright source there, which turned out to be, we measured period, it turned out to be a neutron star. Moreover, it turned out to be a magnetar with very large magnetic field, and it became a very strong source. It wasn't a giant flare, but it was a very, a strong source, which is capable of producing one of those giant flares which come to the Earth. The gamma ray flux can perturb the ionosphere of the Earth. Imagine you have some flare in the Magellanic Cloud, and then the ionization level in the ionosphere here on the Earth raises like if it was a major flare on the Sun. So we are talking about that kind of effect. So these objects are capable of producing, really affecting the Earth. And so this guy happens to be pretty close at about, not in the Magellanic Cloud, it's just at 4 kiloparsecs away. But normally you wouldn't see it. It actually almost disappeared now. So they can hide these magnetars. And it's very plausible that we have a few of them around. We just don't see them. There may be many of them around. We don't see them until they make boom. Yeah, right. Okay, so I really don't have, well, I take another 3 minutes, which I have. Much time to talk about the second part, but I'm also working a lot on pulsar winds. And since the first part of the talk was on the pulsars, not on any other kinds of neutron stars, I thought it's reasonable to mention pulsar winds. And so Chandra X-ray Observatory made really a revolution in our understanding of pulsar winds because it produced all these very pretty nice images, right? And before that, we didn't know how pulsar wind nebulae look like, except for one, maybe, which is a crab. But now we came to realize that there are different kinds of pulsar wind nebulae. And one important distinction is depends on the velocity of the neutron star. If the neutron star is moving very fast, the nebula would look like a bow shock with a long tail, sort of like a comet, if you like. And then if the neutron star does not move fast, you would expect something more spherically symmetric or axisymmetric, right? And so the most famous, yes, is this crab. And crab has been seen before Chandra, but it's only now with the Chandra we can really resolve the fine structure of the crab. And so we had this program to look at the crab with VLA, HST, and Chandra simultaneously in couple years ago. On the same day, actually, all these observations occurred. And now we have a picture of the crab at multiple wavelengths, and it's taken on the same day, which means that, crab is dynamic system. You don't want to look at it at 3 different points in time with different telescopes, because then you're going to get confused. You really want to get a snapshot. So that's what we see here. And you can see that there is a remarkable level of complexity in this system because, so the green one is the optical emission. It mainly traces filaments. Filaments where you have, ionized gas. The blue one is actually near infrared. That's kind of a unique image because there was no high resolution image of the crab in the infrared until that happened. And so that one doesn't have much of the filaments. It traces synchrotron radiation. All right, and then there is a radio, which is red here, which traces, we don't know what it traces because it doesn't look similar to the filaments, and it does not look similar to the optical emission either. So it's a bit of a puzzle. So you can make all kinds of pretty pictures if you replace, say, near-infrared with X-rays, and you can see something interesting here, like two jets appear there. So one jet is at lower energies, which is bent this way, and the other jet is in X-rays, which is bent the opposite way. How would the pulsar have two jets in the same direction? That's something unreasonable for the something which is axially symmetric and rotating. So there are all these kinds of interesting findings. And this is a picture of the crab at the high-resolution picture in radio, which is a really puzzling structure. They don't look all like crab. This is Vela Nebula, which has this double lobe structure in the radio and toroidal structure in X-rays. So there's no double lobe structure for the crab. So some of them are very different. Some of them are actually quite dynamic systems, like this one. If it plays, let's see. Oh, well, it chose not to play. But this jet is actually an interesting, it's like a spiral structure which rotates, and it's possibly due to the neutron star precession. Now, the bow shock ones will be in the next talk. They will be discussed by Noel, so I'm just going to skip those. And they look like tails, really like comets. And this is a very interesting case we are working on now. This is a bow shock, one of those collisionless bow shocks which Jack mentioned in the previous talk. And we know we can see them maybe in X-rays. We know we can see them in H-alpha. But this is a unique case where you see the shock in the far ultraviolet. And so it's not something that has been seen before or expected. And if you try to calculate what temperature corresponds to thermal emission, say, in the far ultraviolet, you would not get this temperature from standard collisionless shock heating estimate. Because we know the speed of the pulsar, so we can estimate the kinetic temperature, and it does not match. So that's something we are working on here. Now, I said that I'm interested also in gamma ray sources because, you know, it turns out that neutron stars account for a large fraction of them. In the Fermi band, it's really, you know, if you look at the gamma ray sky, the galaxy, at the Milky Way disk, you find that those bright sources on the gamma ray sky are actually, many of them are pulsars, and some are supernova remnants. In the TeV range, again, you know, a quarter at least are apparently pulsars with pulsar vein nebulae, but maybe there is another half is also those things. So multi-wavelength observations are critical to understand the nature of these new, really new gamma ray sources, which appeared in the past 5-6 years. We didn't know about that. Those are all the pictures which we didn't have 7 years ago. We had no clue what is gamma ray sky, how does it look like. And so now we are going through these studies, multi-wavelength studies, looking with Chandra and other telescopes, trying to sort things out. And these are just beautiful pictures of some of those very high energy sources where you look at different wavelengths and you try to understand. And sometimes you see these voids, which could be due to the supernova explosion, but we don't see supernova remnant in this case. So some of them are pretty puzzling. In some cases you see supernova remnant, but then your TeV source is sort of well within the supernova remnant, and there is no actually obvious pulsar there. So what's there in the middle producing this TeV emission? Or, that is all open questions which you could study. And so I'm not going to recap what I just said. I'm just going to say that, despite 50 years of research, we keep finding some very, very significant new things, like those hiding magnetars, very hot but old neutron stars. And so that is still a very exciting field. And that era of gamma ray astronomy has been mentioned already by Jack, and it's really here. And when the CTA is built, I think we're going to have a similar revolution to the one which we had after the Chandra was launched. So it's very exciting. And so if you're interested in that kind of science, you talk to me or email me or just come to George Washington University and you'll see where we go. Thank you. If you have any questions, just ask, but you can ask later, because I'm over time. So.
Okay. Thank you.
PowerPoint or what is it?
PDF. Okay. How do I switch slides? It's the PDF, yes.
How do I make it full screen?
There should be an option for that.
Oh, no. Still.
View. Yeah. Oh, good. Go page up. Like 2. Where's page up?
Wait.
Oh.
Switch.
Okay.
I guess it's the first PDF you're trying, right?
I mean, I tested the PDF if it works. You can try it on your Mac if you want.
Mine is showing. Is it showing?
This is it, yeah. So just go 2 slides up.
How do I switch?
Arrows.
Okay, you will have to switch them like.
Okay.
All right. So the final talk today is by Noel Klingler. He's also my student. Sorry. Yeah, and so he's from George Washington University. He's going to talk about a specific kind of a pulsar and a pulsar ring nebula, which is a power shock around the fast-moving pulsar.
Can everyone hear me?
Yep.
Okay, cool. Oh, I got cut off. Today my talk is going to be on deep Chandra observations of pulsar tails, PSR BO355 plus 54. Just some pulsar basics. You have neutron stars, they're about 1.4 solar masses. They spin really fast and make extremely strong magnetic fields, about 10 to the 12, or even sometimes up to 10 to the 14 Gauss. It accelerates charged particles relativistically, and then they radiate synchrotronically, generating X-rays. So here we're looking at PSR BO355 plus 54, and that arrow represents its velocity vector. It moves at about 61 kilometers per second. It is about 1 kiloparsec away, which is relatively far for pulsars. They're usually within less than half a kiloparsec away. And its energy loss rate is about 5 times 10 to the 34 ergs per second, which compared to other pulsars makes it young and energetic. So for our study, we looked at 8 new observations, totaling about 395 kiloseconds of new ACIS data. And we also look at 66 seconds of old ACIS data from 2004. So one of the most obvious and prominent features of this pulsar is that there are structure on many different scales. It has about 5 arc-minute-long tail that spans behind its motion. When you zoom in, you see this region that we call the mushroom on an arc-second scale, and it has the core, or the pulsar, which is somewhere in there, the cap, and then what appear to be 2 stems. The mushroom region, then, now. This is the archival data from 2004. This is a merged diffuse image of our 8 observations, limited to the energy range of 0.5 to 8 keV. You can see that it has a solid conical shape mushroom region, there's a gradual decrease in brightness towards the center, and there's a sharp decrease at the edges here. And of course, you get the bow shock there, giving it a steep beginning. So one of the things we noticed was that there is a variability in the brightness of the sides of the cone on a time scale of about 5 months. So we made these 6 regions here, radiating out, but not including the core. And then we broke our observations into 2 groups of about 135 kiloseconds each. The first one is from November to December of 2012, and then the second 2 observations are about 4 or 5 months later. And we noticed that in these side regions, namely 1, 4, 3, and 6, you get drastic changes in brightness of about ranging from like 10 to almost 30%. Compared with the background only decreased by about 1.3%, and this is after accounting for transient sensitivity and an exposure map, so it seems to be statistically significant. Then we looked at spatially resolved spectra, so the spectra properties of different parts of the nebula. We made the core region tightly packed around where we believe the pulsar to be, the mushroom region, the cap, and then the entire tail, but then we later broke it up into 2 smaller regions to see if there was a change there. And you get slight cooling as you go down the tail because the particles lose energy as they radiate synchrotronically. One thing we want to know is, could the lobe, this area, be resolved in the TeV energy range, which we would... Did you write a proposal for that? Working on it. So then here we wanted to see if those side regions had any different spectral properties. We call them the mushroom ears. And they don't. They're spectrally the same, although the brightness changed. The graded is just from the previous page for comparison. So then this is our pulsar compared to similar ones. This is Gaminga and J1509. Both of these are detected in gamma rays. And these both have similar structure with a more hollow conical shape and this third tail there. And as Oleg was saying before, the pulsar velocity has a big impact on the shape of the pulsar wind nebula. You can have different shapes depending on how fast the pulsar is moving, the direction of the spin axis, and the density of the medium it's traveling in. So then we wanted to know, is emission from the pulsar in the core region unresolved, or is it? So we did a radial profile fit of the real data versus simulated data. And to do that, we ran chart, which is Chandra ray trace, and that simulates a point source based on spectral parameters. And then Marks simulates the detector response. So this is an image of the core region, and this right here would be the mushroom. It's very zoomed in and small bins. And it's almost basically a point source, except when you get to about 1 arc second away from the center, you get small contributions from a diffuse emission. So then here's a picture of our results. This is all of our real data merged, and that's with a blur applied. And then this is the simulated data zoomed in, and we subtracted them to get this residual. And you can see this toroidal structure there, which was not visible before. And this is like right in that region. Very small. So summary of the results. The mushroom region fits an absorbed power law with a slope of 1.4, which is within the range of similar pulsars. Then we divided the tail into 2 regions, and we get the cooling along the tail. The mushroom appears to be stable between the morphology of the mushroom between the archival data and our new data, although the sides dim and the toroidal structure is visible. Our interpretation of the results is it's possible that the spin axis is directed towards us, and that these 2 stems you see would be the 2 jets kind of superimposed on each other, which would be like the same structure as seen in other pulsars, but viewed from this angle, as if we were here looking at it like that. And the mushroom ears, the decreasing on that, the size of the ears is about 7 times 10 to the 16 centimeters, which over about 5 months would correspond with a speed of 0.05 to 0.1 c, which is consistent with flow speeds and wind speeds from other pulsars. So that's what could be happening there.
Thanks.
Any questions?
So is there like a definite point that you like saw this come from, like there's supernova and there's like neutron stars flying away, or like, or is it just
No.
you know where it came from?
No, unfortunately, that would be very helpful if we had a supernova. We could estimate, like velocity of the particle, because now we're just guessing it from the shape of this bowl show. But in some cases, you do see supernova, but not in this case. So,
Yeah. The age of this pulsar is calculated to be about 500,000 years old, and usually the supernova remnant disappears after a couple tens of thousands.
so this one is pretty old, so probably it dissipates the supernova. There was another.
Do you see any cluster nearby?
Sorry?
Do you see any cluster nearby?
Oh, no. There was another question on that end, no?
Do you know if does the morphology have anything to do with the age of the pulsar?
I don't think so. It would probably be dependent upon the velocity vector, where the spin axis is in relation to the velocity vector, and the density of the surrounding medium.
Yeah, that's our working hypothesis, but we don't really know for sure, why some of them are hollow, like empty bowl shocks, and the others, filled, like in the top. So obviously there are two types. And our working hypothesis, that may be orientation of the line of sight with respect to spin axis and orientation of the spin axis with respect to the velocity vector of the pulsar. So that's the hypothesis. There are some very strange ones where you have a velocity vector going this way. This just recently discovered, like a year ago or a year and a half ago. So the pulsar is going this way, it's here, and there is a tail, that's okay, it's reasonable. That's like that, what Snow was showing. But then what's this thing? What's the thing which is, in the perpendicular direction? And this pulsar is going with a crazy speed of, I think, 1,000 kilometers per second, or even more. So you would think that all of this pulsar wind will be pushed behind the pulsar into some long, bright tail. And okay, there is this tail, but what's that one-sided, strangely shaped feature? And the same applies to this pulsar, which is moving again at 1,000 kilometers per second, and then nothing behind in X-rays. There is an H-alpha nebula behind, but then there is a very actually bright X-ray feature in the perpendicular direction, again in one side. These are not known what are these things are, so they don't fit into any standard model. It looks like the ones which move slower, they sort of fall into traditional, in this sort of reasonable hypothesis that everything is going to be behind. But as you get to some critical speed, when it starts moving really, really fast, something happens, and some strange features perpendicular to the direction of motion appear. Yes.
How do you know those perpendicular feature things aren't just at a completely different place than the pulsar?
Well, I mean, there is not much around. If you zoom out, I mean, there's a larger field of view. There is nothing there except for point sources. There is only one extended diffuse feature, and it happens to be right there next to the pulsar. I mean, chance of coincidence is not large, and now we have two cases, and that can't be just coincidence.
What's the lifetime of the electrons that they can transport out if they are from the pulsar?
The typical lifetime would be from 1 to 10 kiloyears for reasonable magnitude. All right, then thank you guys for your patience. Yeah. For your attention. Now, those who go to the happy hour, let's meet outside over there. Otherwise, I'll see hopefully most of you tomorrow.
Can I take this out? Can I take this out?
Yes, just take it out. It might
Do
complain.
we have the half an hour poster session? No?
What?
That's no half an hour poster session? Or it's too late or something?
Yeah, guys, feel free to grab food or coffee that's outside. We'll look at the poster. You're going to collect stuff, so it will take some time.
If you want to go home with free sandwiches.
Yeah, pick the sandwiches. Ashwin, we need to collect stuff carefully. So collecting stuff means we need Noel and Rob and Jeremy. We need to move the posters if they're staying here. If people
For those of you who will not be joining us tomorrow, thank you very much for attending.
Wait a second. If you want to leave, if you have a poster, you want to leave it here for tomorrow as well. So you don't take it home. You can leave it here. Unless it's very valuable. I don't think it's someone going to steal it.
This poster is made of paper. Oh yeah, none of those are cheap, right?
Yes, we need to, if people don't take posters, then in any case, we need to move poster stands inside this room, like next to this wall.
Sure.
So let's see if they gonna take them or not, and then.
Right?
Yeah.
Right. So, can we, I mean, is this room going to be locked? Because if we could leave the poster stands in here, that'll be the most convenient, right?
What are we doing?
Yeah, we're gonna leave them here.
Okay.
We're gonna just bring them inside the poster stands.
Do you want us
in
to
this
start
room.
then? We'll start that by the way.
What are we going to do?
Let's wait a little, maybe people
Yeah.
picking up
What
their
should we do with
posters.
all
That is up. Secretary is going to take care. I mean, unless
No.
you want to take
No, I'm
take
fine.
as much as you want.
I had, I think, 4 bagels. Bagel outfit.
Are you, Kalvir, are you going for the happy hour or you're busy?
I can join you for a bit, yeah, but I do actually have to be at another place in about 30 minutes.
Oh, that's probably then not going to work because it will take time for us to.
Right. No, well, I mean, where are you going? Tonic?
Probably, yeah, locally.
I'll see if I can pop over. All right. I mean,
Give me a call then.
I'll do my
If
best.
you are-
Yeah. Okay.
If you are looking for us, then give me a call.
Yeah. Okay. All right.
There's something missing. Okay. I wonder. No, laser is a good point. Yeah. So
Missing, like, as in...
like, what is that? I mean, it doesn't feel like it belongs. Oh, maybe it does. Do you think it belongs here? It's strangely painted. Is it USB stick or it's not? What is this? What is
This one already has one?
That has. That is complete.
This is the right one?
For sure, the right one.
Yeah, I can think so.
What is
Not sure.
Europe?
Oh, one of my good friends' girlfriends does like auditing for the NSF, and I was so confused because there was a number I didn't know, and it was about Ice Cube, and I'm like, what? But I guess she just audited the Ice Cube collaboration and sat down with like 2 of the big.
Oh,
big
wow.
shows. She's like, it seems like your cup of tea. Yeah, it's pretty interesting actually.
Speaking of Ice Cube, we just published, or rather, we just put on archive a collaboration paper between the LIGO collaboration and the Ice Cube collaboration, and it's got to go down as one of the longest author lists
I'm
on
sure,
paper
yeah,
because
what
it's
is it?
something like 1,200 people.
Yeah, it surprised me. That's ridiculous.
It's 6.5 pages for authors and institutions.
That's insane.
the paper is only like 13 pages total. It's like a third of the paper is authored.
I think this suck is